All right, sorry for the interruption. We'll continue where the last video abruptly ended. Where we're at here is we started with an integral, x times ln of x all squared, and we use integration by parts once so far. We let u equal ln of x all squared, and then dv had to be equal to the remainder, which was x times dx. We integrated dv to get v. We took the derivative of u and rearranged it to get du, and then plugged it into our integration by parts formula and did a little bit of simplifying. At this stage, we've replaced our original integral with a function minus a new integral. And that new integral is definitely better than what we started with. We started with x times ln of x all squared, and now our new integral is x times ln of x not squared. In order to proceed, we have to use integration by parts a second time. This sounds horrendous, but it's pretty normal. So here we go. And what I want to do is I want to find the antiderivative of x times ln of x. I'm going to do that in this box at the bottom, and then whatever I get for it, I'm going to plug it in up above for that integral. Now we're going to use integration by parts a second time. I'm going to use the LATE acronym again. The LATE acronym tells us what the most likely good choice for u is. We look at the letters LATE, and look at the components of our expression. If we see a log, first letter of LATE, then that's what we let equal to u. If there's no log, now we look for the next part, algebraic part, we let that equal to u. If there's not one of those, then we look for a trig, and we'll let that equal to u. Here we do have a log, so I'm going to let u equal ln of x, our log function. dv has to be everything else inside the integral. The integrand and the dx, when we multiply those together, they have to be u times dv. So dv is going to be x multiplied by dx. All right, now this formula for integration by parts, if we recognize that this integral in the box there, that's equal to the integral of u dv, then the integration by parts formula says that we can rewrite that as uv minus the integral of v du. So I'm going to get the components that we need. Du by dx is 1 over x, just taking the derivative of u. I want to get du all by itself, so I'm going to cross multiply by dx. So du is equal to 1 over x times dx. And then for v, I'm going to integrate dv. Integrate both sides of that expression. So the integral of the left side is equal to the integral of the right side. Every time we do this, we always get v on the left-hand side. This time on the right-hand side, we get 1/2 x squared, antiderivative of x. And that's going to get plugged in for v in both parts of our expression on the left-hand side. Okay, so we have u times v, so ln of x times 1/2 x squared. Careful, right in the right spot. Minus the integral of v du, 1/2 x squared times 1 over x dx. Okay, so let's plug that in. I'm going to go back to our main calculation. I'm going to plug that in. 1/2 x squared ln of x all squared minus, so the calculation that we just did said that that integral, the 2 over 2 cancels. So we'll have ln of x. Well, no matter how hard I try, I'm not going to get to fit on one line. So I'll just write it all underneath here. Minus ln of x times 1/2 x squared minus, I'll clean up the last part of the integral there in the box. I have a 1/2 that can be brought out front, And we have an x squared on top and an x to the power 1 on the bottom. I can simplify those. It's just an x dx. And now we've replaced the integral of x ln of x with the integral of just x. So we've simplified it further. Let's clean up a little bit before we integrate. 1/2 x squared times the ln of x all squared minus 1/2 x squared times the ln of x not squared minus the integral minus 1/2 integral of x. Well, be careful, it's plus because I'm subtracting the outside of that bracket, and I have a subtraction inside, so I have a negative times a negative, so a positive 1/2 integral of x dx. Then we can integrate. Antiderivative of x is just 1/2 x squared. We've done that a few times in this problem. x squared. Now we've got a big plus c, and miraculously it'll fit on one page. Just going to copy those first two parts and then simplify the last part. I have a 1/2 times a 1/2, so 1/4 x squared plus c. That's our final answer. So hopefully, if you're mortal, if you're a human being, seeing integration by parts for the first time, you should be unhappy with what just happened, the gigantic mess that was created. But what we're doing is we're using a sequence of integration by parts steps to reduce the complexity of the integral that we're working with. We hit it once with integration by parts, it becomes simpler. We hit it again with integration by parts, it becomes even simpler, simple enough that we can just quote the answer. Just what is the antiderivative of x? That's the philosophy behind using this approach. When it works, it sometimes works in a messy way, like inside this example. Here's an example where we're asked to use integration by parts only once, to use one cycle, so-called cycle of integration by parts, so to not fully solve the antiderivative. I'm going to write the first step of this is recognizing that x cubed e to the x integrated. If we're using integration by parts, then this thing here is equal to the integral of u dv. And the integration by parts formula says that I can rewrite the integral of u dv as uv minus the integral of v du. So that's IBP. Now for the not substitution, for what are we going to let u and dv equal to? We're going to go to the late acronym. We don't have a log, but we do have an algebraic. So that tells us that u should equal x to the power of 3. dv has to be everything else. X cubed is already taken into account, but the e to the x dx hasn't been accounted for yet, so that those pieces get lumped into the dv. I'm going to take the derivative. Du by dx is 3x squared. Rearrange to get du. Du is equal to 3x squared times dx. So that's that part out of the way. Now for the second part, I have to integrate dv. Oh, not thinking very well. Okay, so I'm taking the antiderivative of dv, I'm going to get v. Taking the antiderivative of e to the x, I'm going to get e to the x. And as always, we hide the plus c. Okay, and then those pieces are going to get plugged into the integration by parts formula. So u is equal to x cubed. And then v, we found, was e to the x. Minus integral of v, which is e to the x, once again. And then du is 3x squared dx. And then this can be cleaned up a little bit. So the x cubed should stay in front, x cubed e to the x. And for the second thing, we can put the 3 in front of the integral. We can put the x squared in front of e to the x, put it in standard form. And that's our answer using integration by parts once. We were only asked to do it once. Use IBP once to transform it, so we stop here. We're done the instruction, but we're not done the integral. If you want to continue this, if you want to fully solve, do integration by parts again and again. You'll have to do it twice more. The next round of integration by parts, you let u equal x squared this time. Then du is going to be 2x dx. Do the v part, v is equal to e to the, or dv is equal to e to the x dx, so v is going to be equal to e to the x. Plug it all in. You'll get a new integral. This time it'll be x e to the x. Then you do integration by parts one more time, and you will reduce that integral down to just the integral of e to the x, which you can integrate directly. We had to do integration by parts 3 times. There was a power of 3 on the x. I'll leave it to your imagination to tell me, or to consider, how many times you'd need to use integration by parts to integrate this. X to the 7 times e to the x. You need IBP 7 times. I lied. It says you leave it to your imagination, but I don't think much imagination is needed. So depending on the problem, if you want to fully solve it, you may need to use several rounds of integration by parts. We've seen that there's 2 different species of integrals, broadly speaking. And I don't mean methods to use to solve integrals, I mean integrals that are fundamentally different. One type of integral outputs a number, and the other type of integral outputs a function. We just worked on examples of using integration by parts on indefinite integrals, integrals that don't have bounds of integration. The output is always a function, that plus c, that arbitrary constant of integration. If we look at integrals that have bounds, we can also use integration by parts with a small modification of the formula. So I'll show you what that modification is. So I'll put it in this box here. IBP for definite integrals. Here's your formula. That your integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral from a to b of v du. So all that we're doing to create this formula is we're taking the 2 components that come out of the integration by parts formula for indefinite integrals, and we're just evaluating both of those pieces from a to b. We're taking our uv piece, evaluating it from a to b, and we're taking our integral of v to u and putting bounds on that integral, the same bounds that the question started with. So I'm going to go ahead and use this formula and this approach to find the antiderivative of ln of x evaluated from e to e cubed. So for this problem, our late acronym, LATE, we have a log. U is equal to ln of x. That means dv is equal to everything else, which is just dx. That's all that's left. We've taken everything into consideration for the u part, except the dx. I'll take the derivative of our u. du by dx is 1 over x. Rearrange. du is equal to 1 over x times dx. For dv, we'll do the same thing we always do. We're going to integrate both sides. The antiderivative derivative of 1 times dv is just v. The antiderivative of 1 times dx is just x. So we're going to plug that into our IBP formula. We get uv evaluated from e to e cubed minus the integral from e to e cubed of v du. So let's plug in u and v. U is ln of x. V is x. And we're going to evaluate this from e to e squared minus integral from e to e cubed. V is x. And then du is 1 over x dx. So just subbing in all those pieces. Let's clean this up. Actually, look at the first part. We can evaluate it. We have the ln of e squared times e squared for the top bound being plugged in. Now I'm going to plug in the bottom bound minus ln of e times e. And then we have minus the integral from e to e cubed of just 1 dx. We have an x on top and 1 over x and multiplied by 1 over x, so that's just going to be x over x, which is 1. Let's clean up a little bit. Ln of e squared, we can use the cancellation law, we get 2. Ln of e is just 1. And then for the integral here, we have the antiderivative of 1, which is x. So x evaluated from e to e cubed. Typo. Oh, e cubed. I have a typo over here too. I gotta fix, so I'm gonna go up and fix my typo right now. My apologies. No one was here to yell at me. I have to yell at myself. Typo. It's a 3. So we have a ln of e to the 3 is a 3 using the cancellation law times e to the 3. And I'm paranoid. I'm going to double check everything above. Everything looks okay. All right. So we have 3e cubed minus e cubed minus e. So 3e cubed minus e cubed plus e, and we can collect like terms. So 3e cubed minus e cubed is 2e cubed. Minus e plus e cancels, and we just get 2e to the power of 3. Which makes me a little bit nervous. But we'll stick with it. Send me an email or post on the forums if you find any errors in any of these calculations. All right, the last normal example before we get to the abnormal examples. We have a definite integral going from 0 to pi over 2 of the function x times the sine of x. So we're going to attempt integration by parts with late. We don't have any logs. We have a trig and we have an algebraic, but the algebraic a becomes before the trig t. So that means u is equal to x and dv is equal to sine of x dx. I can take the derivative of the substitution. Du by dx is equal to 1. And then that means du is equal to dx. For dv, we're going to do the usual. We're going to integrate both sides, and we get v is equal to negative cosine of x. Our integration by parts formula for definite integrals, we have uv integrated from 0 to pi over 2 minus the integral from 0 to pi over 2 of v du. So let's plug in those pieces. U is x, v is minus cosine of x, and then that's evaluated from 0 to pi over 2 minus integral from 0 to pi over 2. V we found was negative cosine of x, and du is just dx. So let's pause for a moment, look at this. What have we done? We've replaced the integral of x times sine of x with an integral of cosine of x. Definitely nicer. I'm going to clean this up before evaluating it. Negative x cosine of x evaluated from 0 to pi over 2. For the next part, I have two negatives multiplied together, so those will cancel and give me a positive. Integral from 0 to pi over 2 of cosine of x dx. Now let's do the evaluation of the first piece. We have, for the top bound, we got negative pi over 2 times the cosine of pi over 2. And for the top bound, minus 0 times the cosine of 0. Now we have the integral to worry about. The antiderivative of cosine of x is sine of x. And that's evaluated from 0 to pi over 2. So I'm going to double check something here. Sine, cos cancels. Cosine, okay. Wasn't the answer I was expecting, but that's okay. So we have negative pi over 2 times the cosine of pi over 2. Cosine of pi over 2 is 0, cos of 90 degrees, plus 0 times cosine of 0 is 1. But it's multiplied by 0, so it doesn't really matter. Plus the next part, sine of pi over 2 minus sine of 0. I wasn't expecting such a nice answer. We get 0 plus 0. Sine of pi over 2 is 1. Sine of 0 is 0. We get 1 as our answer. Usually we don't get very nice answers with definite integrals that require integration by parts. But hey, this time we did, so that's something, I guess. Well, I'll stop here. That ends the normal examples for integration by parts. In the next video, I'll go through abnormal examples or non-standard examples that are a little bit better for tests.